it's money for polarities is just okay. It's not that good. Any commercial project in the United States will get, I don't know, hundreds times more. In Silicon Valley, and some if you sell it to people, investors. And in Russia, science, it's different because if you get money, you have just no get them. You're very poor, so you can be rich. So anyways, maybe only. Okay. Okay, so good afternoon, PCS members and friends. Today we have a scientific seminar, and our scientific host today is Professor Sergey Plakh, who will introduce our speaker.
Yeah, okay, oh my God. So, welcome everyone. It's a great pleasure to have Professor Boris Altshuler with us as a seminar speaker. He gave several talks, at least not many, like during this time of our interaction. And let me still say a few words about Boris to those of you who don't know him that well. He finished his bachelor in 76 and his PhD in 79 at the Leningrad State University and Leningrad Institute for Nuclear Physics, respectively, which is now located in the city of St. Petersburg. So this was Soviet times. Then he moved on. He was a research fellow at the Leningrad Institute of Nuclear Physics. And until 89 and in 1990, he became a professor of physics at the MIT. Now we are jumping onto another continent, where he essentially stayed since, being a fellow of NEC laboratories in America, and then a professor of physics at Princeton University from 96 to 2005, and since 2005 as a professor of physics at Columbia University. He has lots of awards. He has, well, not maybe last Onsager Prize, Hewlett Packard. Those are very nice things, I guess, and Dirac Medal, Oliver Buckley Prize, I think all things you heard about, Humboldt Research Award, and so on, Edmund Stoner Award. And he published a lot of papers, especially a lot of very important papers. One or a few of them, or maybe not just a few, but quite a couple of them are on Many-Body Localization, which he initiated with colleagues in 2005. And which caused an amazing productivity or production of lots of numerical and other results in the world. Today, maybe you'll hear something related to that. He will speak to us about scaling theory of the Anderson Localization revisited, which I think will be related to Many-Body Localization. So the floor is yours, Boris. Let's welcome the speaker.
Okay, thank you very much for this introduction and even more for having me here. It's one of my beloved places in the world. And what I wanted to discuss today is some kind of looking back for almost 50 years and correcting some kind of misunderstanding or certain things we left behind at that time. So what I will present is a result of 3 papers. 2 of them are published in the Proceedings of National Academy of Science, and the third one is still there and will be published in a while. And let me start first with the just quick historical remark. So, yeah, I want to acknowledge my collaborators, Vladimir Kravtsov, this person with whom we work for many years, almost 40 plus, and who is one of the leaders in this direction, And then there is a group that at that time was in Trieste, a group of people. Karl Vanonin is now in Princeton. And the last paper was done in collaboration with the group from Slovenia, from Ljubljana, and the leader is Lev Vidmar. And they are from this Joseph Stepan Institute. So the history, of course, starts in 57 when Phil Anderson wrote this paper, which brought him later a Nobel Prize, although it was not met very enthusiastically by the community. And the statement he made was that if you consider a quantum particle subject to some disordered potential, then it's possible when potential is strong enough that quantum states of this particle will be localized in space, and if you will let it start at a particular point, it will not go too far and will not be distributed all over the available world. And as I told, this story was not very enthusiastically accepted, but later it turned out that there is a lot of deepness in this problem, and a lot of different experiments can be understood in these terms. And one would think that theorists would jump and work on it, and it actually took quite a bit. So this is 57, and in 78 or almost in 79, there appeared a paper which some people know as Gang of Fours paper. Abraham, Anderson, Licciardello, whom thought I couldn't find, and Ramakrishnan, they formulated a scaling theory of localization, which at that time was indeed a revolution. And let me very quickly remind you what is the mainstay. So beforehand, one of the ideas that people entertained was so-called the minimal metallic conductivity, which was proposed by Sir Neville Mott, who claimed that there is so-called minimal metallic conductivity, and it means that conductivity of the system of these particles, if states are localized, equals to zero. If its states are extended, it's not zero, and at the transition point, conductivity changes abruptly, and the statement of this for people in 78 was that it's better to speak about conductance of a whole system rather than conductivity, and this conductance has an interesting property that it's basically dimensionless, because conductance, not the conductivity, can be measured in units E squared divided by Planck's constant, regardless to the number of dimensions. And this is a result of their studies, that one can write dependence of this dimensionless conductance G as a function of system size in a following form, that derivative of the logarithm of conductance over logarithm of system length is some function only of the conductance, not of conductance and system size, and this is quite non-trivial statement, as you will see in a short while, this led to more or less a clear picture of what we should expect from this transition. So, first of all, this meant that there is nothing like minimal metallic conductivity. And second, if you believe in this relation, then you know asymptotics of this beta function, and dependence of G is more or less of this type. So when conductance is large, beta function tends to the value which depends on number of dimensions D, and it's equals to D minus 2. So in 3 dimensions, it's 1. If you would consider problem in 4 dimensions, it would be 2. And in 2 dimensions, it should approach 0. And it simply follows from the fact that if you think your conductivity is constant, then conductance scales as system size to the power D minus 2.
So about the picture, why there is this circle for 4 dimensions?
No. This circle is
the
disregarded. I don't know how it appears.
The other one, yes.
And another one, why it's emphasized even in 4 dimensions?
No.
Not 3?
The only thing I wanted to emphasize is that important is this point where this beta cross 0. And I will explain, but this please disregard. So I just wanted to tell that again from old arguments of Anderson, it followed that in deeply localized states, conductance is not only small, but it decays exponentially with system size, which if you will take derivative, you will find that this beta function should scale as logarithm of the conductance. Okay, so this was the picture, which meant the following. So these are points, critical points, where this derivative vanishes, which means that if you manage to get to this point, you can increase system size, and your conductance will not change because derivative equals to 0. And according to this equation, conductivity will be getting smaller and smaller as system size to the power 2 minus d. And if you start a little bit to the right of this point, so if you just took small system and your conductance is a little bit bigger than this critical one, then you will have positive beta, and sooner or later you will get into the this metallic behavior when conductivity will scale, conductance will scale like this, and conductivity approach constant. If you start to the left of this point, you will again have beta negative, and sooner or later you will get into this regime.
Sorry,
Yeah.
I ask you one question. When a G is very small,
Yeah,
Does it mean that we don't have a clear relation between conductivity and the conductance?
yes, because your conductance is decaying exponentially. So it will mean that conductivity is ill-defined. It's not the property of the material, but the property of whole system, and depends very strongly on system size. So there is no reason to introduce this as an observed. Okay, so this is the picture, and it was called, and I will use this many times. It's called as one parameter scaling theory, because you have this G, and G is the only parameter. Now, what is important is the derivative of this beta function at the critical point, because this derivative actually determines localization lengths or correlation lengths, depending on whether you start with conductance above or below the critical value, and this power nu is exactly the inverse derivative here, and this distance depends on how close you are to the critical disorder, but I will speak about it a little bit later. And please remember this, if we believe in this one parameter scaling, then for any observable which you can imagine, this observable, if you know its dependence on conductance, then its dependence on system size is always like this. It is the same function of the conductance, which is function of the system's size itself. And it means that in principle, you are not obliged to be using only the conductance. You can use any other observable and write similar renormalization group equation with, of course, different beta function, but still in the same form, where this new beta function doesn't depend on that. Please, if it is confusing, please ask me questions. Okay. Now, what followed from this consideration was the fact that in 2 dimensions, all states are localized. You can show that beta is always negative unless you have strong spin orbit, but this is not what I want to discuss today. And since beta is always negative, doesn't matter what is your original conductance, it can be very big, but still when you increase system size, you will go into localization, not speaking about one-dimensional case when it is even easier to get to the localization, which is was known since 50s, that all states in one dimension are localized. But what I want to concentrate today on is nature of the transition. And at low dimensions in 2 and 1, transition doesn't exist, and it starts from high dimensions. And in order to make some calculations, people invented so-called 2 plus epsilon expansion. So the situation is the following, that not only there is this scaling theory proposed by this gang of force, but very quickly, people came up with a strong analytical support for this theory because they brought some kind of heuristic arguments, and this support was based on so-called nonlinear sigma model, which is basically effective field theory where conductance enters as some parameter of this model and can be renormalized in a way similar to other phase transitions. And although this is quite peculiar field theory because what you would call normally order parameter is some supersymmetric matrix which does not have any clear physical meaning. Nevertheless, you can make the same arguments as you do for usual phase transitions in statistical physics. And one of the instruments developed there was getting into the fractional dimensions. And it turned out that the easiest thing to do here was to consider your system in a space with dimension 2 plus epsilon, when epsilon is small. So remember, the limiting value is d minus 2. So if you are into the 2 plus epsilon dimension, your limit will be epsilon, and the critical value of the conductance will be large. It will be inverse epsilon. So here will be logarithm of the epsilon. Yeah.
I had a question. So in this plot that you are showing, where is the disorder strength?
The disorder strength determines where you start in your in this curve. So if disorder is critical, you are in this critical point. If disorder is stronger, you are above, below. If your disorder is weaker than critical, you're above.
But was there a formula that related G with the disorder strength?
Yes, this is basically this. So G naught is your starting point, and GC is critical, and the difference is proportional to the difference. I will come back to that. Okay. So there is this 2 plus epsilon expansion. Critical value of the conductance is inverse epsilon. It is very large, and one can analyzing leading or even subleading terms in epsilon calculate many things in this model. And indeed, this was the main reason why people believed that although we're dealing with three-dimensional transition if we study system experimentally, but qualitatively what we understand in from this epsilon expansion is probably correct for higher dimension. Yeah, and I'm not going to speak about it today. It's a story of its own, but if you want to learn about this approach of nonlinear sigma models to these problems of disorder, I strongly recommend this wonderful book of Kostya Fetov, which discuss all this issue. Okay, so we have these results for small epsilon, but what about d equal to 3 or d bigger than 3? And if you remember, for ordinary phase transitions, there is low critical dimensions, which is in this case 2. So below low critical dimensions, the phase transition does not exist because fluctuations destroy it. But there is also higher critical dimension where you can use mean field. But in this case, it's completely unclear what does it mean, because as I told, your order parameter is not doesn't have physical meaning. And
sorry, can you remind again? You said it's kind of like a matrix, the order parameter?
yes, not only matrix, but supersymmetric matrix.
But the matrix, which means it's not just one, so to say, number,
Yeah.
but it's a whole set of number. Can we
to make it even more dramatic, it can be supersymmetric, which is more stronger foundation, but some people use replica. So it's matrix which size at the end should be put equal to 0. So, but nevertheless, I mean, this theoretical structure exists, but what happens in high dimension up to now was basis of serious theoretical discussions. People from field theory once in a while come with some strange proposals. Okay, now about disorder. So now we are approaching to what I want to discuss. The plain ground of this field is so-called Anderson model, which he
I will try to get rid of this.
What's the problem?
Oh,
Okay.
You just go ahead.
Yeah. This model, which Anderson proposed in his original paper, is the following. I probably here discussed it many times. You start with a lattice, some lattice. It can be square or triangle or whatever you want, and you are considering the tight binding model on this lattice. So each side can host a state for a particle. But in contrast with textbook tight binding model, the on-site energies are not all equal to each other. If they are all equal to each other, you will get usual band structure, but they are random and independent random values, and they are not correlated. This is the model, and they are uniformly distributed. Of course, you can modify this model many times, make distribution not uniform but Gaussian or whatever. You can take into account correlations and so on, but let's restrict ourselves by this simplest original version. And in addition to these on-site energies, as you usually have in tight binding model, you have matrix elements of the hopping between two states when they are nearest neighbors on this lattice. And this is basically the model, and what we now believe after so many years of studying this model is that for disorder stronger than certain critical, we have insulator, if we have in mind charge transport, and from the point of view of quantum mechanics, all states are localized. If we have disorder that is smaller than critical, we have extended states which are metallic, and yes, in 2 dimensions, this WC equals in 2 and 1 dimensions. It equals to 0 in 2 plus epsilon. This critical dimension is critical disorder is probably proportional to epsilon, and in 3 and higher dimensions it's something, and we have this insulator to metal transition or localization to extended states transition. And what happened?
Yeah, now you.
Maybe you need to
Just deep comment.
click once, yes.
Okay.
Try again.
No,
Try
Yeah. Now,
chaotic.
what I would have in mind today is extension of this Anderson model to a graph, because a lattice, in some sense, is also a graph, but very particular one. But in principle, for any graph which is characterized by matrix M, which is 1 for a pair of sides that are connected, and 0 for any pair which are not connected. And what we consider is sum of this matrix with certain diagonal matrix with random and uncorrelated and uniformly distributed diagonal matrix. So this is quite straightforward generalization. And indeed, people were thinking about it for quite a while, but it became really, really exciting and important when it became interesting to study many-body systems that are close to integrability, and then you have sites determined by the quantum numbers of the quantum integrable system. So each state of integrable system is characterized by a point in this space of quantum numbers, and if you perturb it by some perturbation that violates integrability, this perturbation provides you with matrix elements between these original states of integrable system, and that's why this perturbation establishes a graph M. It tells which states are connected and which are not, and you are also reducing yourself to something like Anderson model with in a certain graph, and the graph is specific for this many-body system. Some difference is that from the original Anderson model is that hopping matrix elements are also not equal to each other, but this is what it is, and we have in mind this type of problems. And just to give you an idea of these many-body states, this is a graph for a model that people very often, probably to my taste, too often study for so-called XXZ spin chain, where people are trying to understand this phenomenon of many-body localization. This is a hypercube, which is a graph that corresponds to quantumizing chain. So I will say a few words about this. And this is something which we studied quite a bit numerically, this is known as random regular graph, where you build it in the following way. You fix a number of which is called connectivity, and with n sides, you make a graph where each particular side is connected with k other sides, but with which ones it is more or less randomly chosen, and you have whole ensemble of this random regular graph, which you can study and study the Anderson model on that.
Can you go back one second?
Yeah.
So this XZ spin chain,
Yeah.
is that an integrable case? Or is it already the perturbed?
No, it becomes integrable without disorder, if I'm not mistaken.
But the links here, which you show here, are the links because you said before that you have this space of points and the space of quantum numbers. Is that the space here?
Yes.
Then what are the links? The links are induced by disorder?
Yes.
So in the absence of disorder?
No. Let me better discuss this because I have pictures, and then this I actually stole the picture somewhere, and probably I can do it, but it will eat all my time. So let me explain how you get a hypercube for quantumizing chain. So you have a Hamiltonian, which consists of two parts. One big part is Hamiltonian, whatever you can imagine, built from only Ising component of the spins. So you have n spins, and sigma z is z component, and this is interaction. I'm not even thinking about nearest neighbor, not nearest neighbors. All of them are here, and I can add, if you want, also a parallel field. It still will be some kind of Ising-like model, and this is integrable because each sigma z commutes with this Hamiltonian, and as a result, if you start with certain sequence of these sigmas, which can be in principle, let's say 0, 1, or 1 and -1, whatever you like, it will, this so-called bit string will be conserved forever. So set of any sequence of zeros and ones is an eigenstate of this Hamiltonian. And this term, which is proportional to sigma x, is perpendicular field, and it does not commute with sigma z's, and as a result, this term violates the integrability. And if you recall that sigma x is sigma plus sigma minus, what this operator does, it actually flips the spin from 0, it makes 1, from 1, it makes 0. And all in all, what we get Anderson model on n-dimensional cube, because each bit string, each set of sigma z's determines a side in n-dimensional space, and this perturbation actually connects two sides which are different by flipping of one of the speeds. So each side has n connections, and you have altogether 2 to the n states on this hypercube, and you can speak in terms of whether your eigenstates are localized or extended over this cube. Okay, now let me do the following. If we are extending our set of problems from ordinary finite dimensional lattices to some generic graphs, we probably need to think about something different from the conductance, because what is conductance is of hypercube with dimension equal to 100 or 1,000. And what I will use will be a substitute of conductance by the quantity called fractal dimension of the state. And as you will see, this concept is applicable to a much broader range of problems than this conductance.
Well, you could have introduced a conductance notion in the original Hamiltonian, couldn't you?
Yes, there are several.
Except you have long range hopping, you say you don't. Oh, yeah, you could, right?
Oh, you definitely can. Basically, it's sensitivity to the boundary conditions, but you can rewrite it. If you know a set of eigenstates and eigenenergies, you can write equation for the conductor. But there is something simpler. I don't know. Can you?
We see
Yes. Okay. So let's do the following. Suppose we have sides that are labeled by this I, and we have an eigenstate of our problem, which is a certain function of I. And there are many of these eigenstates, so in principle, I could write here a label alpha. And this state is normalized, so sum of psi squares is equal to 1. Then what I will introduce is what is called Shannon entropy, which is sum of psi square log psi square with sign minus, because psi, of course, psi square is, of course, smaller than 1, so log is negative, but this sum is positive. And as you will see, in general case, it scales at large n as something proportional to logarithm of the number of sides. And the prefactor, which in this dependence, I will call D1, which will be first fractal dimension. So this is a clear definition, and this can be straightforwardly calculated if you diagonalize the Hamiltonian.
Sorry,
Yeah.
Can you go back, please?
Yeah.
So psi is an eigenfunction.
Yes.
So
In principle, you can apply it to any wave function, but I will think about eigenfunction.
1. Now, when you change the system size, you change your graph, and you change all the entire set of. So how do you continue? And what's you have to maybe fix something, some energy or something like this in order to know how you.
No. What is done actually is the following. You, of course, take not one realization, but many realizations and preferably many functions in each realization, and calculate the average value of this entropy, and then you calculate derivative for divided by log n.
Average of all eigenenergies, or you?
No, you normally you choose some three
Specifics of
Yes,
this type.
yeah. Yes, but in principle, if what you can do, you can make an average only over several states, and then ask yourself, is it self-averaging or not? And we can discuss it is sometimes yes, sometimes not. But in principle, it is something, of course, which makes sense only in average. Okay, now what is physical meaning of this fractal dimension? And I like the following object, which is nice to have in mind, which I call support set. So our function is normalized, but I can ask myself how many states I need to take in order to satisfy normalization up with accuracy of some epsilon. And this I also can do. I can, for example, take epsilon 10 to the minus 3, and then make this calculation and select the states with biggest value of psi square, and have this set and calculate this number, which depends, of course, on epsilon, because if we tend epsilon to 0 at fixed n, we will, of course, get this size equal to total number of sides. However, if we change order of limit, so consider first limit n to infinity, and then if you want tend epsilon to 0, you sometimes will get, of course, ns proportional to n, but it is possible that it will be ns to some power which is smaller than 1. So you will get in this support set, which is basically a set of sites where this wave function is present, it will be infinite in the limit n to infinity, but it still will be measure 0 of all the states. And so it's nice to have this idea that basically D1 is determines you how many states, how many sites are filling the presence of this particular state. And I don't want to speak too much, but I still have to remind you that in principle, this is first and probably most important example of this Shannon entropy of so-called renew entropies, which are a set of numbers determined by this parameter q and determined like this. So instead of psi square log psi square, you have this definition. You can check that when q approaches to 1, you have Shannon entropy, but in general, you also have this renew entropy proportional to log n, and you have this prefactor, which in general depends on q. Now, what are the states that we have in mind? So if states are ergodic, which means that there are no states where which determine the normalization, and there are no really empty states. So psi square is an each state of the order of 1 over n, and then you have for here 1 over n to the power q, and you have sum of n such states. So you have here n to the power q minus 1. You take log, you cancel, and what you have d equal to 1. Now, if you have states that are localized, then again, all your psi's are what you have here is only finite number of important terms. So this sum does not depend on n, and that's why derivative over log n is equal to 0. So dq equals to 0 for all q's. And there can or cannot be states where these fractal dimensions are neither 0 nor 1, but something in between. And in principle, these numbers depend on q, and these states are known as multifractal. And you will see that in order to describe the critical behavior of the transition to localization, we need this to have this multifractality in mind. Okay, so this is just to demonstrate. Sorry. Okay. So this is what happens. Critical value of W in for three-dimensional Anderson model is 16.5. So this is 15, and here you have state for a cube of this size, which is this state is ergodic, d equals 1. If W is bigger, you have localized state and d equals 0. And exactly at the critical point, people speak about multifractal states with intermediate value.
So, sorry, Boris, multifractal because this dq depends on q.
Yes, but today I will speak mostly about d1. But yes, it depends on q, and the difference is substantial.
I see. So if it were not dependent on q, then you would just call it fractal.
There are special models which are not multifractals when all the q's equal to each other, but they are not, they exception.
Okay.
Okay, so let's recall this fact that we can use anything instead of conductance. And at the beginning, we were thinking about possibilities like this fractal dimension, or maybe another fractal dimension. Another possibility was so-called R parameter, which was introduced by Ganesian and Hughes, and it's actually a nice numerical way of analyzing the spectra. So you take two consecutive spacings. These are eigenenergies. What you do, you take two consecutive spectra and divide the smallest one by the biggest one. And this division allows you not to worry too much about the unfolding the spectrum, about worrying about the density of states changing as a function of energy. And for this ratio, you have certain limits for Poisson distribution and for Wigner-Dyson distribution. And again, for example, normalize it in this form, you will get parameter that also could be used as this parameter of the scaling theory. But it turns out that fractal dimension is much more natural and easier to think about.
Why? If you can say
Yeah.
in a few words.
I don't know even how to approach our parameter analytically. Although for fractal dimensions, we know what it is into plus epsilon, and there are a lot of other arguments that we can take into account. So what I'm drawing here is a cartoon of what you would expect for this scaling when you take derivative of logarithm d over logarithm of the volume. So for d-dimensional space, it's L to the d, but in general, it will be n. So as we know, d changes from 1 to 0, and 1 corresponds to ergodic state, and 0 to the localized state. And what you will guess is that your beta function should behave in this form. So it should be positive at large enough fractal dimension. It should vanish at certain, should be DC here, at certain critical value of fractal dimension, and then become negative so that fractal dimension will, if you manage to get through this critical point, will then scale to 0. So again, if you start with d bigger than critical value, you will end up with 1. If you start with d smaller, it will be 0. And as I told, it's basically follows one-to-one from this picture.
And if I was to take a one-dimensional system from the left,
Yeah.
how would this curve look here?
Yeah, I can show you 2 dimensions, but
Well, will it always be below the act?
excuse me? No, just give me a minute, and I will show you 2-dimensional, and then we can discuss. Beforehand, I just want to make one statement that indeed we know critical dimension DC for 3 dimensions, and with certain accuracy good enough for this picture, we know it for 4, 5, and even 6. It's results of numerical calculation.
You mean for Anderson model, right?
For Anderson model. But there is one consideration that is important to make, that if you think about your support set in the real space on your lattice or on your graph, then on the lattice, the dimension of this support set will be equal to number of dimensions times fractal dimension of this support set. And since this dimension small ds cannot be smaller than 1, because smaller than 1 means that it cannot be a single connector. It will always consist of infinitely far parts, and infinity for parts cannot form the same support set. So the conclusion that we make is that D1 should be bigger than 1 over D, and according to this calculation, it slowly but surely approaches this 1 over D limit, which is quite surprising, though, that indeed this dimension is in high spatial dimension of the support set is always close to 1.
This is at the critical point.
Yeah. Now, this is answer to your question. This is result of numerics. This is D equal 2, D equal 1 will be something like this, but it was not calculated. And this is perfectly agreeing with this one parameter scaling. Indeed, you start somewhere on this curve, and it takes you down as on the elevator to D equals 0.
So is this a fit or it's some analytical prediction?
Analytical prediction
Red curve here
is good for D close to 1, where all this weak localization technique works, but it cannot go too far here, of course, because.
So this is related to weak localization treatment.
Yes. Okay, now go to 3, because actually this is what we want. We want to understand behavior near the critical point. And what we see is that if we just take beta as a derivative of log D over log n, then what happens is, as Volodya Kravtsov likes to claim, is that this behavior grows here. So you start not on this curve, not on this arc, but somewhere outside, and then your evolution depends on original conditions, but when you keep increasing your system size, it approaches, they all collapse in the same curve, either for small d or for large d, but close to the criticality, we have this kind of mix.
This is for the 3D.
Boris,
This is for 3D.
Are these functions analytically calculated, or are they just fits?
No, we don't have analytical form. This is pure numerics. Today, I am 99% experimentalist.
Okay, but are there some analytical analysis of this?
No, I'm not. You can make some effort. I don't think it was done to do something in 2 plus epsilon, but
Okay.
I don't think even this is possible, that this is not beyond the 1 over epsilon, 2 plus epsilon expansion.
Okay.
Because this is
returning to your beginning, is there an upper critical dimension? Is there some analysis approaching some mean field-like theory, or what?
No, there is nothing like upper critical dimension as far as we understand. And there is no mean field theory because, as I told, there is no physical meaning of the order parameter.
Yes.
The order parameter is some, not even a matrix, but some supermatrix or matrix in a replica limit which size equals to 0. So this is strange theory from this point of view, but let me put it in the following way. What it suggests that there are some irrelevant operators which we have not took into account. And when you are close to the critical point, what you see this here is evolution of these irrelevant operators. But as far as I understand, there are many of them, and probably some efforts can be done, and we can learn something about these curves analytically. But when you go further and further in dimension, or in a different problem which I was planning to speak about, but it looks like I don't have too much time, then you will see something very different. So it's 5 o'clock. Can I have another 15 minutes, or shall I give,
No, let's take another 15.
Yeah. Okay. So this is what you have, and what conclusion is that far from the criticality, this one parameter scaling actually works very well. It's not it's just pure numerics that demonstrates it very well, but in the critical behavior is very different. And you can see it even from the raw data of dependence of the fractal dimension on system size, because usual one parameter scaling would tell you that there are either curves where D1 increases or decreases, but these curves quite clearly demonstrate a certain minimum which corresponds to zero of this derivative, the zero of the beta function. Okay, now this is about the random regular graph, and let me skip this part. So this is what you have for random regular graph. This becomes even more dramatic because indeed when W is smaller than WC, for your flow, you have presumably this part of the behavior. So beta is negative, so D decreases, but then it approaches to zero. It approaches it with infinite derivative, so it can pass it in a finite RG time, and then it approaches this one parameter arc.
Sorry, can I ask a question? Where is connectivity here on this plot?
This particular curves were done for k equals 3, but in a sense, you can think about connectivity as something that evolves in system size. Well, you see, if you have
this is not random regular graph, it's qualitatively.
no, but on small scale, qualitatively and random regular graph are very similar to each other. It's only large loops that differ them, but these loops give you a difference. And what I want to emphasize is clearly here we have critical curve, not critical point, which is zero, but a critical curve that corresponds to critical value of disorder, and it tells you how you approach to here. And this is basically the results for both large dimensional Anderson model and Anderson model on a regular random regular graph. You have this arc, which is single parameter, and you have this critical line, and everything to the upper right goes to the approach a single parameter scaling, which drives you to 1. Everything below takes you to this part, which is gets more and more negative. And at the beginning, we thought that here also something like this, but it turns out, this points where it crosses 0 corresponds to minimum in dependence of d of log n. But what I want to tell that it turns out that instead of getting to minus infinity, beta simply approaches a constant when d goes to 0, and this constant determines the localization.
Question. So large D means large D Anderson model, right?
Well, large.
What means large D?
No. Large means bigger than 2.
Yeah, but Anderson.
Anderson.
So now, but then you should see the same deviations from single parameter scaling also if you were to go back to the original conductance.
Yes.
You should see.
Yes, but it was actually seen. There was a story where people were calculating critical exponents in 3D Anderson model, and there was a certain number, I don't remember exactly. And then a group led by Slevin, our friend, they suddenly published a paper which changed the critical exponent by, 15%. And the statement was that they took into account some irrelevant operator. I cannot really explain you, but it turned out that you can see certain anomaly which you have to get rid of, and this is what people saw. I will maybe very quickly tell you. Let me skip this K3. So what you have is the following evolution. So you start at a certain point, and what you need, suppose you are in above critical critical curve, and W is smaller than WC, you start somewhere here, and first thing to do is to get to the point A. But point A corresponds to 0 beta function, and it means that moving around this point, which plays a role of some critical point, if you are originally close to criticality, it takes you quite a long time. And then you still go before you get to point B, which is substantially closer to this one parameter arc. And then what happens is that you have another part of your journey, which is dictated by this one parameter scale.
But if you are in point A, I mean, then the derivative is 0, then you don't move anywhere.
No, you see, what you need to do is to integrate this equation d log L equals to beta, and depending on how beta behaves around this point, either integral converges or diverges. And for example, for Cayley-3, where the derivative is constant, it indeed diverges. That's why for Cayley-3 you will never cross this point, and you always have multifractality, but it's not quite clear. We discussed it with Alexei, and it's still quite a problem how to check it numerically. I mean, for Cayley-3, but in this case, it is finite time, but still this time is critical when W approaches to WC. So all in all, in order to get from point O to point A and from point A to point B is critical, and it is proportional to 1 minus W over WC to the power minus nu when nu is 1/2. You can make your own calculation, and you will trust me because everything is.
What is K? E is a function of D and K.
K is connectivity, which is K naught to the power L. And what happens with time from B to C actually depends on what we don't know, how this arc behaves close to zero. It can behave linearly or as a square root. If it is it behaves linearly, then this time will be with nu equal to 1, not 1/2. If it is square root, it will be still 1/2. And to me, is more likely, and we have some other toy models which support it, that we basically have two critical exponents, and one is dictated by vicinity of this point, another by vicinity of this point, and this is kind of unusual situation. And another thing which I only mentioned is that in principle, ratio of n to n critical and L to L critical, where n critical is the value is L critical is analog of correlation length, and n critical is correlation volume, but this ratio is not a function of this ratio. And it turns out that this evolution is behaves as linear scaling as a function of L to LC, and this evolution as a function of N to NC. So something that people saw numerically, but it is also quite non-trivial. And if I still have 2 minutes, let me very quickly tell you about very recent results. So what we know is that there is connection between localization and spectral statistics. Namely, for extended states, we expect Dyson spectral statistics. For localized states, it is more like Poisson. And usually people immediately recall this distribution of spacings that have to this particular distribution. And what is important is that spectral statistics are by construction basis independent. So there is this connection, and for the first sight, it looks like in this critical case, there can be nothing interesting, because both of these distributions decays either exponential or in a Gaussian way, and big gaps are very improbable. So there will be something in between. And why do we have to recall? But if we go to larger than spacing energy scales, then something interesting appears. So there is some, I forgot how it's called, maybe
Number variance.
Lumber variance or delta-3 statistics or whatever. So you take a certain interval in energy, you calculate number of levels, and then you compare fluctuations, mean square fluctuation of this number with its average value. And it turns out that these two quantities are proportional to each other. And for Poisson, delta n square exactly equal to an average. For Wigner-Dyson, repulsion is so strong, spectral rigidity actually drives this high to zero. And it looks like there are a lot of different calculations that show that in this multifractal critical or whatever states, we have something that is called quasi-Poisson when this high is between 0 and 1, or semi-Poisson. And there is another way of speaking about this. If you study the spectrum form factor, which is sum over e to the energy times tau with certain prefactor, you have at times which are much shorter than Heisenberg time, this form factor actually forms a plateau, and value of this plateau is also equal to the same quantity high. And what is the statement is that this sum of this high and fractal dimension is always equal to 1 in the critical regime, but also in the two limits. So if d1 equals to 1, high equals to 0. If d1 equals to 0, high equals to 1. But this is correct in the critical point as well, which is surprising because as we discussed, high is invariant under basis rotation, and d1 in principle depends on the basis. So the guess is that we are speaking about minimizing fractal dimension over all possible bases.
Can you remind
Yeah.
what was tau on the x-axis?
Tau is time. So you sum e to the I minus I energy tau. Okay, this story is the following. I don't know why piece of formula disappeared. First, Chalker, Kravtsov, and Lerner actually made in 2 plus epsilon expansion calculation and came up with this formula that high is equal to 1 minus d2 over 2. And in fact, it was correct because for small criticality, for small epsilon, 1 minus dq divided by q is constant. So they could, instead of 1 minus d2 divided by 2, write 1 minus d1 or 1 minus d4 divided by 4. But later, Bogomolny and Giraud actually analyzed certain long-range matrix model and claim that this is correct, high equals to 1 minus d1, but for high dimensions, it's not correct because this dependence is not valid. And this is results of calculation made by this Ljubljana group of Lev Vidmar, and this thick line is combination of high calculated by the variance and by the form factor. As you can see, they are indeed pretty close to each other, and this black curve is dependence of 1 minus dq divided by q. So you can see that in 3D orthogonal and 3D unitary, in 4D orthogonal and 4D unitary, the fact that this is correct only at q equal 1, but correct with accuracy, which is probably better than equivalence between the two ways of calculating. So in all this Anderson model, we conclude that 1 minus d1 is indeed equals to high. And there is one model which is turned out to be very useful, so-called the banded random matrices. This is definition of the dependence of Hij over difference between I and j, and Mij is just some independent random quantities. And this is what you can see. The crosses are high calculated in different form, and the box is 1 minus d1, and the red box is 1 minus d2 over 2. And indeed, in the range of parameter b, which corresponds to small multifractality, they coincide, but when you reduce b, the difference is substantial, and this high equal to 1 minus d1 identity is perfectly observed.
Boris,
Yeah.
so can you go back, please?
Yeah.
So if I try to use chi instead of the dimension d as a parameter, or which tells me where the transition happens, will it work, or can I compute this chi and tell in the 3D Anderson, for instance?
Probably. The point is that it's not so easy to numerically calculate high. Of course, if you have this identity, then at least to find the critical point and critical behavior, you can calculate high. But the problem is that you have this compressibility in principle depends on the width of the window. It cannot be too big because you start to feel that your band is finite. It cannot be too small because, yeah, so it's some intermediate. And the same with this plateau.
But these are numerical issues. But
Yeah.
in principle,
In principle, yes.
because d1 is always basis dependent, as you said, so you don't know whether you're actually working in the proper one, right?
Yes,
Because
yes.
it's probably the one which is the smallest one, but how do you know that that's the smallest one?
Yeah. Yeah, but let me add a little bit more to that, and I will let you go. So, as I told, it is easier to calculate this R parameter than compressibility. And it turns out that compressibility and R parameter are somehow connected in a universal way. So if you know where you are between Wigner-Dyson and Poisson, and you know your symmetry, the unitary or orthogonal, you can tell, so this is dependence on B, and since high is also function of B, R is function of high.
What was B?
B is parameter for of this model, banded random matrix. And what Kravtsov did heroically, he actually calculated these dependencies of D1 over R for these banded random matrices, and it was semi-numerical, so he had to let computer calculate certain sums, but nevertheless, we have these two curves. One is for orthogonal, another for unitary version of this random banded matrix models. And then having these two curves, you can try to check other models. And it turns out that indeed you take, say, 4D orthogonal Anderson model, and you see that it is indeed close to what we have in this theoretical curve, and for 5D unitary, it's still pretty good. At least distance is not bigger than the error. And there are all other models which also can be checked. And up to now, all our checks work pretty well. For example, and this is my last statement, it's very interesting to study what happens in a quantum Hall case on the step. So you remember, quantum Hall is a set of plateaus between integer values of Hall conductivity, but between plateaus is a step. And people, and in the step, there is critical behavior of sigma XX. And what people really want to know is what kind of critical behavior we have. And there are some discussions, theoretical, but numerically, D1 was calculated with amazing accuracy, like 4 digits. And it was a group of Evers in Germany, and we asked them, what about our parameter? They said, oh, great idea, let us calculate. Then they send us a certain number, which was pretty well fitted into this plot, and we asked, can we, with reference, publish it? There was no answer. Up to now, no publication, no answer. I don't know what is going on, but I strongly expect that indeed for quantum Hall, this relation still works. And to finish with, for me, the most exciting is looks now to understand what is connection between this relation between D1 and high, how it manifests itself for classical system. And I think it's somehow connected with the spectrum of Lyapunov exponents, and this is what I'm trying to convince Sergei to think about. Thank you very much.
Thank you, Boris, for this fantastic lecture. I think we can still take a few very important questions before we move on for food, which is waiting outside, I guess. Questions? Everyone is tired?
Can I ask a
Yeah,
quick
Bruce.
question? So when you had those hair-like structures in this one parameter plot, so the way you did it is that you choose numerically, I'm asking. So you choose a disorder strength, and then you change system size to obtain one of the hairs?
Yes.
Okay.
Yes.
And then changing the disorder strength will either go in one direction or in another direction?
Yes. So there is a critical curve, and you are, if you increase disorder, you move to one direction. If you decrease disorder, to opposite direction.
Okay, Barbara?
I just want to make a remark. I mean, I looked at compressibility with Chai and the Wigner-Dyson model, and compared to R ratios, and there you've really big discrepancy concerning the transition points, because in the R ratios, they are seen much later than for compressibility. You immediately see it. The transition from ergodicity to the non-ergodic region, whereas for R ratios, it's somewhere close to the Anderson localization transition. So it's not a good.
Can we discuss it with?
Yeah, this would be a very good idea. Yeah.
Good.
Okay.
More important questions? Not the case. So let's thank Boris again. Thank you very much.